66 million years ago, on an ordinary afternoon that no living creature had any reason to fear, a rock roughly the size of a mountain slammed into the shallow sea near what is now the Yucatan Peninsula. It hit with the force of billions of nuclear weapons detonating at once. The impact vaporized rock instantly, triggered earthquakes that shook the entire planet, and threw so much debris into the atmosphere that the sky itself turned dark for years. Within a matter of months, roughly 3/4 of every species on Earth, including every non-avian dinosaur that had ever walked the planet, was gone. They were not wiped out for being weak or for failing to adapt. They were wiped out because they only had one home, and that home got hit. Here's the uncomfortable truth most people never sit with. Right now, in this exact moment, every single human being who has ever lived, every book ever written, every language ever spoken, every memory anyone has ever had, exists on one planet, one rock, orbiting one star, in one corner of one galaxy. We have never had a backup. Not once in the entire 200,000-year history of our species have we had anywhere else to go if something went catastrophically wrong here. And the scientists who study existential risk for a living will tell you quietly and carefully that this is not a theoretical problem. It is a mathematical certainty waiting for a date. So the question stops being whether humanity will ever need a second home. The real question is whether we build one before we need it or after it is too late to matter. This is the story of the search for that second home, and the extraordinary science being done right now to find it. Before we get into how close we already are, if this is the kind of question that keeps you up at night in a good way, go ahead and hit subscribe right now, because this channel exists for exactly this conversation. We track the missions, the discoveries, and the science that are quietly answering one of the biggest questions humanity has ever asked. Where do we go if Earth stops being enough? Subscribing costs nothing, and it means you will not miss the next discovery in this story because there is always a next discovery. Okay, let's get into it. People tend to assume that planetary catastrophe belongs in science fiction. It does not. In 1908, a chunk of space rock roughly 40 meters wide entered the atmosphere over a remote region of Siberia called Tunguska and detonated with the force of roughly 1,000 Hiroshima bombs. It flattened 80 million trees across more than 2,000 square kilometers of forest. Had it arrived 4 hours later, given the rotation of the Earth, it would have leveled the city of St. Petersburg instead of an empty forest. In 2013, an object barely 20 meters across entered the atmosphere over Chelyabinsk, Russia, undetected until it exploded, injuring over 1,000 people from the shockwave of shattering glass alone. Nobody saw it coming. Our detection systems, even today, only reliably catalog objects large enough to be civilization-ending, and even then, coverage remains far from complete. And asteroids are only one item on a much longer list. Yellowstone sits on top of a supervolcanic caldera capable of an eruption that would blanket much of North America in ash and drop global temperatures for years. Gamma-ray bursts, some of the most energetic events in the known universe, could in theory strip away Earth's ozone layer if one occurred close enough and pointed in our direction. Then there are the risks we are creating ourselves. Engineered pandemics. The slow accumulation of nuclear weapons across an increasing number of states, runaway climate feedback loops, advanced artificial intelligence systems whose long-term behavior nobody can fully predict yet. Individually, each of these risks might sound survivable, but add them together across centuries and the math becomes sobering. Prominent physicists and cosmologists have spent decades arguing publicly that a species confined to a single planet is, by definition, a species with an expiration date it cannot control. This connects to one of the eeriest open questions in all of science, something astronomers call the Fermi paradox. Given the sheer number of stars and planets in our galaxy alone, the odds strongly favor the existence of other intelligent civilizations somewhere out there. And yet, we have detected exactly 0 confirmed signals from any of them. One proposed explanation is called the Great Filter, the theory that there is some barrier somewhere along the path from simple life to a spacefaring civilization that almost nothing successfully gets past. Some researchers suspect that barrier might be exactly this problem. A young civilization simply runs out of time on its homeworld before it manages to spread beyond it. If that is true, then finding and building a second home is not an interesting side project. It may be the single most important task our species has ever faced. So what actually makes a world usable as a backup home for humanity? Scientists studying habitability generally look for a specific combination of features, and losing even one of them tends to be disqualifying. You need a stable orbit inside what is called the habitable zone, the narrow band around a star where temperatures allow liquid water to exist on a surface, rather than freezing solid or boiling away entirely. You need enough gravity to hold on to a meaningful atmosphere over geological time. You need a magnetic field strong enough to deflect the stream of charged particles constantly blasted outward by stars, because without one, solar radiation slowly strips the atmosphere away entirely, which is essentially what happened to Mars over billions of years. You need protection from radiation at ground level, because unshielded exposure over years is lethal to human biology. And ideally, you need existing local resources, water ice, breathable elements, usable soil, because hauling everything a colony needs across interplanetary or interstellar distances is simply not realistic with current or near-future technology. Every candidate world scientists are currently evaluating gets measured against this checklist, and every single one of them fails at least part of it. The question researchers are actually working on is not which world is perfect. It is which imperfect world or which engineered alternative gives humanity the best odds of survival. The most obvious candidate, and the one that gets the most attention, is Mars. It is the planet in our solar system most similar to Earth in terms of day length, seasonal cycles, and surface geology. NASA's Perseverance rover has spent years exploring Jezero Crater, a site scientists chose specifically because it was once an ancient lake bed, and the rover has been caching soil and rock samples for a future mission to bring back to Earth for detailed analysis. Its companion, the small helicopter Ingenuity, proved that powered flight is achievable in an atmosphere less than 1% the density of Earth's, a feat many engineers doubted was even possible before it actually happened. But Mars is not simply an empty Earth waiting for us to move in. Its atmosphere is roughly 1/100th as thick as ours, composed almost entirely of carbon dioxide, and offers essentially no protection from cosmic radiation or solar particle events. Mars lost its global magnetic field billions of years ago, and without one, any atmosphere humans tried to build up would likely be stripped away by the solar wind over geological time, exactly as the planet's original atmosphere was. Surface temperatures swing from a relatively mild daytime high near the equator to nighttime lows cold enough to freeze carbon dioxide directly out of the air. Long-term human habitation on the open surface, without heavy shielding, simply is not viable right now, which is why serious mission planning increasingly focuses not on domes under an open sky, but underground. Mars is riddled with lava tubes, tunnels formed by ancient volcanic flows, some of them wide enough to fit an entire city block. These tubes offer natural shielding from radiation and micrometeorite impacts, and researchers have specifically identified candidate tubes near the Arsha Mons and Pavonis Mons volcanic regions as future habitat sites. Combine that with confirmed subsurface water ice at both poles and in mid-latitude regions, and Mars starts to look less like a red desert and more like a planet with the raw materials for a genuinely self-sufficient settlement, provided humanity is willing to live mostly underground for generations, while any terraforming effort, which would likely take centuries at minimum, slowly plays out above them. Private efforts are already racing to make this a near-term reality rather than a distant dream. SpaceX has been explicit for years that the entire purpose behind its Starship program is enabling a self-sustaining city on Mars, with founder Elon Musk repeatedly framing multi-planetary settlement as an insurance policy for the survival of the species rather than simply an exploration goal. Whether that specific timeline holds is genuinely uncertain. Spaceflight has a long history of schedules slipping, but the underlying engineering problem, building a rocket large and reusable enough to move the mass a real settlement would require, is now being actively worked on rather than merely theorized about. Closer to home, the moon is playing a very different but equally important role in this story. Nobody seriously proposes the moon as humanity's final backup home. It has essentially no atmosphere, no meaningful magnetic field, and its surface swings between scorching daytime heat and brutally cold 2-week-long lunar nights. But its proximity, roughly 3 days away by current spacecraft compared to months for Mars, makes it the ideal proving ground. NASA's Artemis program is explicitly designed around this logic, establishing a sustained human presence at the lunar South Pole, specifically because permanently shadowed craters there are now confirmed to contain substantial deposits of water ice. Ice that can be split into oxygen for breathing and hydrogen for rocket fuel. The moon lets engineers test closed-loop life support systems, radiation shielding techniques, and in situ resource extraction methods, in an environment that is brutal but only a few days from rescue if something goes catastrophically wrong, rather than months away like Mars would be. Every habitat design, every question about long-term low-gravity exposure on the human body, every lesson about growing food in lunar regolith gets tested here first. In that sense, the moon is not really a backup home at all. It is the training ground for building one somewhere else. There is also a third path entirely, one that does not depend on finding or terraforming any planet at all. Physicist Gerard O'Neill proposed back in the 1970s that humanity could build enormous rotating cylindrical space stations using centrifugal force to simulate gravity along their inner surface, populated with real soil, real sunlight, redirected by mirrors, and a fully engineered ecosystem inside. These structures, often called O'Neill cylinders, could theoretically house tens of thousands of people each, built from materials mined directly from asteroids or the moon, rather than launched at enormous cost out of Earth's gravity well. The appeal of this approach is significant. It completely decouples human survival from the specific conditions of any single planetary surface. You are not waiting millions of years for Mars to develop a magnetic field, and you are not limited to whatever habitable real estate the universe happens to provide you. You are building your own from scratch. The engineering challenges remain enormous structural stress at that scale. The sheer amount of raw material needed, radiation shielding thick enough to actually matter, closed-loop agricultural systems capable of feeding thousands of people indefinitely without any external resupply. But asteroid mining technology, still in its early stages, is advancing quickly, and companies and space agencies alike are increasingly treating near-Earth asteroids not as scientific curiosities, but as raw material depots for exactly this kind of large-scale space construction. Interestingly, some of the most useful research for any of these habitats is not happening in space at all. It is happening right here on Earth, inside sealed structures built specifically to simulate the isolation of a distant colony. Biosphere 2 in the Arizona desert sealed a small crew inside a fully enclosed miniature ecosystem back in the 1990s. And although the mission ran into serious problems with oxygen levels and crop failures, it taught engineers hard lessons about just how difficult closed-loop life support actually is to balance. More recently, the HIC's habitat on the slopes of Mauna Loa in Hawaii, chosen because its cracked volcanic terrain closely resembles the Martian surface, has hosted multiple simulated Mars missions lasting up to a full year, with crews living under the same communication delays, the same resource limits, and the same psychological isolation a real Mars crew would face. Even Antarctic research stations, some of the most remote and self-sufficient outposts humans have ever built, now feed directly into space agency research on crew psychology during long, dark, isolated stretches with no possibility of quick evacuation. None of these are a backup home by themselves, but they solve a human factors problem no telescope or rover ever could. Meanwhile, a parallel and equally urgent search is happening much farther from any thought of human colonization, out in the icy moons of the outer solar system. Europa, one of Jupiter's 4 largest moons, has a surface of solid ice covering what scientists are now highly confident is a liquid water ocean underneath. An ocean that may contain more liquid water than every ocean on Earth combined. Saturn's moon Enceladus goes even further, actively venting plumes of water vapor and ice particles directly into space through cracks near its south pole, plumes that spacecraft have already flown through and sampled, detecting organic molecules and evidence of hydrothermal activity on the seafloor below, activity strikingly similar to the deep ocean vents on Earth. where many scientists believe life itself may have first originated. Neither Europa nor Enceladus will ever host a human backup home. The radiation environment around Jupiter alone would be lethal within hours on an unshielded surface. But these moons matter enormously to this story for a different reason entirely. If life is found in either of those hidden oceans, independently evolved life with no connection whatsoever to Earth, it would answer one of the oldest questions in science. It would tell us that life is not some improbable cosmic accident that happened once, in one place, by extraordinary luck. It would tell us the universe generates life readily, wherever the right conditions exist, which dramatically raises the odds that somewhere among the billions of planets in our galaxy, there is another world capable of supporting not just microbial life, but us as well. And that search has already produced results nobody expected even 20 years ago. As of now, astronomers have confirmed more than 5,000 planets orbiting other stars, and a meaningful number of them sit inside their star's habitable zone. The TRAPPIST-1 system, a small cool red dwarf star roughly 40 light-years away, hosts 7 roughly Earth-sized planets, with 3 or 4 of them positioned in a zone where liquid water could theoretically exist on the surface. Proxima Centauri b, orbiting the nearest star to our own sun, sits tantalizingly within its star's habitable zone as well. Though red dwarf stars come with serious complications, they flare violently and unpredictably, potentially stripping away atmospheres over time in ways scientists are still working to fully understand. Further out, Kepler 452b, commonly nicknamed Earth's older cousin, orbits a sun-like star at a similar distance, though its exact size and full makeup remain an open question scientists still debate. The James Webb Space Telescope has fundamentally changed what is possible here. By analyzing starlight as it passes through a planet's atmosphere during a transit, JWST can identify the chemical fingerprints of specific gases, oxygen, methane, carbon dioxide, water vapor, and critically, combinations of gases that should not coexist unless something, ideally something biological, is actively producing them. Finding oxygen alongside methane in a planet's atmosphere, for instance, would be extraordinarily difficult to explain without life, because those two gases react with each other and destroy one another over time unless something keeps replenishing the supply. Scientists call this kind of evidence a biosignature, and the hunt for one, a single unambiguous biosignature on a planet outside our solar system, is one of the most closely watched frontiers in all of modern astronomy right now. Beyond biosignatures, there is an even bolder category researchers watch for called technosignatures, evidence not of simple life, but of intelligent civilization, unusual patterns of light that might indicate massive artificial structures, atmospheric pollutants that only make sense as industrial byproducts, radio signals with patterns too structured to be natural. None have ever been confirmed. But the search itself, coordinated through projects that continuously scan enormous swaths of sky, represents humanity actively listening. Just in case someone out there already solved the problem, we are only beginning to take seriously. Here is where the story runs directly into the hardest wall of all: distance itself. Proxima Centauri b, our nearest potentially habitable exoplanet candidate, sits roughly 4.2 light-years away. That sounds close until you remember what a light-year actually represents. The distance light itself travels in an entire year, moving at nearly 300,000 kilometers per second. Voyager 1, the fastest and farthest human-made object ever launched, has been traveling since 1977 and still has not covered 1,000th of that distance. At its current speed, it would take Voyager roughly 75,000 years to reach Proxima Centauri, and it is not even pointed in that direction. Closing that gap requires propulsion technology that does not yet exist at any usable scale. Breakthrough Starshot, a research initiative backed by prominent physicists and technologists, has proposed accelerating tiny gram-scale probes to roughly 20% of the speed of light using massive ground-based laser arrays, which could theoretically reach Proxima Centauri in about 20 years rather than tens of thousands. But that approach works for a postage stamp-sized probe, not for a spacecraft carrying human passengers, life support, food, and the shielding needed to survive decades of exposure to interstellar radiation and dust at extreme velocity. For human beings to physically travel to another star system, the most seriously discussed options remain deeply challenging. Generation ships, enormous self-sustaining vessels, where the crew that departs is not the crew that arrives, with children and grandchildren living and dying entirely inside the vessel across a journey lasting centuries, raise brutal questions about genetic diversity, psychological stability across generations who have never once seen a planetary sky, and the sheer engineering reliability required to keep every system functioning perfectly for hundreds of years without any possibility of outside resupply or rescue. Suspended animation, sometimes called cryosleep, remains an active area of medical research. And while short-term induced hypothermia is already used in some emergency medicine today, the kind of extended, safe, reversible suspension needed for a multi-decade voyage is still firmly in the research stage, nowhere close to solved. Which brings the story back to where it started on that ordinary afternoon 66 million years ago, when an entire branch of life on Earth learned, far too late, that having only one home is a fatal design flaw. We are not the dinosaurs. We can see many of the risks coming, or at least most of them. We can build detection networks, calculate orbits decades in advance, and in theory, develop the technology to deflect an incoming object before it ever reaches us. Something NASA already proved was possible with its DART mission, which successfully altered the orbit of an asteroid moon in 2022 through a deliberate kinetic impact. But awareness alone does not solve the underlying problem. Every plan discussed here, a self-sufficient city under the Martian surface, a rotating station built from asteroid material, a confirmed biosignature on a planet 40 light-years away, a propulsion breakthrough that finally makes interstellar travel survivable, exists somewhere on a timeline measured in decades or centuries, not years. And the risks this entire search exists to answer do not wait politely for humanity to finish its homework first. That gap between how urgently we may eventually need a second home and how slowly we are currently building toward one is the real story unfolding behind every rover landing, every telescope image, and every habitat design sketch being drawn up right now by engineers who understand exactly what is quietly at stake. Because somewhere out there, whether it is beneath the ice of Enceladus, inside a lava tube on Mars, in a rotating cylinder built from asteroid metal, or on a rocky world circling a star we can barely even see, there may already be exactly what we are looking for. The only real question left is whether humanity finds it and builds it in time.